question, you can even ask me in the meantime, so it's no problem. So, this is actually the joint work of my PhD student and me. He already advanced and published some paper about this, so this is, let's say, already quite well-known things. Here we make some simple tests. Simple test from this material, we made the bending, and here is with the angle 90 degree. It doesn't look like, but it is, because it's the focus is not in scale, yeah, in vertical and horizontal. And what's happened during the bending? You have, of course, here you have the tension residual stresses. You have here the compression residual stresses, and also because this material is metastable austenite, you have matrixed structure. But of course, because you're doing the bending, you have always neutral part which remain austenitic. And so during the fatigue loading, you have the process that with the fatigue crack growth, also the crack tip, recently the materials change properties from austenitic to matricitic, and so this is the actually interesting issue for analysis. How look like this our task? So we can see here. I will try to run this test. Yes. So this is on our test machine, which should work. Oh, sorry, back. So when you start to let's say combine loading, you have this profile, and to start actually to make tension. So your load.
There's no video.
No video. Oh, sorry. Oh,
Don't do this twice, do it once.
okay.
What is goal?
Maybe it's related
Seconds.
to
I don't know.
So, what's happened? Of course, you have the tension and the bending at the same time. Here is actually the pin, so it's the spring for rotation. And we try to actually, additional tensile stress comes here. And this is actually becomes a more critical region. And also, you change the geometry, because the movement from, for example, from this green line on the tip come to this blue line. It is a couple of millimeters, so it changed actually the geometry for the test. And now
it was pre-bent, yeah?
yes, it was
It was
pre-bent.
pre-bent, and then you start doing this.
And then actually we try to open, yeah. And it will be now possible to see the movie. You will see that this part, where it's matricitic structure, actually has a different stiffness, and then you will have let's say ununiform deformation. It will not open like that. It will be so it will matricite remain here because you have no matricity in this side. So we actually also performed the analysis of microstructure. This is the grain. It is the steel in equilibrium condition. This is here the chemical composition which you have in this material. And by using the formula, you can calculate for this chemical composition and the transformation also by temperature. From about 85 degrees already this metastable austenite can go to martensite. And the solution is typical, like in the group. You have the austenite, like gamma. So this is the different structure in the crystal structure. Then you change to martensite epsilon, and then later you have the stabilized martensite alpha tree. So this is actually how this process works. But you know that with transformation of martensite, you have to bigger volume, and with bigger volume introduce the additional stresses in this material. So this is actually the point. Oh yes. So this when you bring the test from the, let's say, virgin material, then you have the engineering curve. This is this black line. That you have the yield point, and you have here the maximum tensile stress, and then you have here, of course, the necking, and then the fail. The stress diagram is looking like that because you consider the break points, you consider this tension, and you got that, let's say, the fracture stress is more than 1,000. But of course, the yield point for engineering is here. We want to actually see what's happened during the tensile test. During the tensile test, you have transformation of martensite. The highest transformation of martensite you have in the middle. It's a more narrow spot because the transformation is higher, and lower, let's say, in point D, this is section D, and we cut this specimen, which is unbroken completely, in order to determine the concentration of martensite and to follow the correlation with the hardness, because also change of the properties from austenite to martensite change the hardness of structure. So, this was actually our task. So first you can see the section B. We made the metallographic analysis, and with this section, yes, we use the microscope, and with graphical analysis, this red, what you can see here, is actually already some martensite inside, and the computer calculates about 11% of martensite phase on the surface, and also we measured the weakest hardness in 0.1. It was 363 for this deformation which you have. We actually calculate deformation with respect to the change of the diameter of the specimen. So the next one is, let's say, in the point B. Of course, you have more martensite and also increasing the hardness, not much, but it's increasing, so it's definitely increase. And also in the state, in section A, you have the 1.73 through deformation, and the hardness is 388, and almost half of the martensite on the structure is calculated by computer. So this is actually what we have here, and okay, yes, we actually have the three sections with the different, let's say, the bending. One was with the 5 millimeters depth. Here you can see it for 10 millimeters. So, depth. And now we compare also with our results. We put the model, which we got from the tensile test, we put in the abacus, and try to simulate this process of bending. So this is the first stage of numerical work, and we see that we get quite good correlation between our three experiments, and also this dashed line here is we got by finite element computation and simulation. So we did actually not only for 10, also for 5 and 15 millimeters of was actually the last highest deformation bend point. You see here it's metallographic samples where we have measured in this peak point, we measure the hardness over this section in order to determine the concentration of the martensite over the section of this section. This is actually cut as a small piece. And here we have also the third part, which is 50 millimeters actually deformation.
Sorry, your model has already accounted for the martensite transformation, or was
no.
So just with the original?
This is the point.
Okay.
We actually use the true stress strain curve.
So you decoupled it, so you
That's
decoupled
right.
the stresses
That's
and
right.
then look at the market.
We don't play with the
No,
change.
I'm fine, simple terms.
Yes, yes. Just the tensile properties, but it seems when you get this combined curve, because in this curve you already have some markers inside, but actually computer doesn't know that you have markers without times. You put just the values, and then with simulation you got this result here, of course. So this is now we did the simulation, and now it is only the quarter of the samples. So because in the middle point, here is the middle point, you have the highest stresses, and we only will now consider this tip here. This is half of specimen, it's another side, and the second half is on another side. This is actually the banded specimen, and you can see that this is equivalent deformation. In this point is highest, because in this point we also have the tension of residual stresses. And now, when we got with our results, it is for all these 5 millimeters bending, 10 and 15 millimeters bending, and here you have the equivalent stress, and you can see that this equivalent stress for numerical work, actually it is here. It depends, of course, how depth you put, 5, 10, or 50 millimeters, but also we here have oscillation with hardness, which we get by measurement, and we can see that hardness how it's going to change in on this level. So this is now we have correlation between compression and tension, because the tension is on the steep side, this one, and here in the envelope side we have the compression during the bending. But you can see that it's got equivalent stress on the same range in compression and the tension side. Of course, in the tension you have the higher equivalent stress here on this side. So this is now that we have some correlation between stress and hardness exists. So the second thing is now we want to put this hardness, and here is now for 5 millimeters bending in these blue points, for 10 millimeters bending is yellow, and white rounds are for 50 millimeters bending. Actually, everything is on the one line. It only depends on the stage how far you are going with this bending. So it is always testing the same material and the same behavior. And also here you can see that suddenly after two strain is about 50%. It's 0.5. You have got one plateau. Yeah. And this is what we measure on these samples, which we made the metrographic analysis. And you can see, of course, the highest is the deformation in A, because it's on the neck, lobus diameter. And here you can now to put this from computer analysis, tomography analysis, we put the points from optical. It is some correlation between these values which you measure from the surface and also with the martensitis content. And hardness is not after 50% linear increasing. That's actually you got the plateau of this value. So if we going now for the next slide, actually the geometry parameters which we should consider in our analysis. Because when we start with the loading, we are here in the B position, and when you start to and the initial distance between pins is A0, and then start to actually to rotate, and you come in position A prime. So this is here, and also you change this D position to B prime position. So now you should consider the changing of moment, because moment has the most influence on stress which you have on the tip. And of course we are looking just in the exact middle point, where is the highest equivalent stress we proved by numerical. And also we proved that actually the crack really starts in the middle here, because we use the heat treatment. And with heat treatment we colorize this crack when you start. That means H has no influence, but you have in the middle the cracks start. This is the first crack, it is darker, and this is the last crack, which is more yellow, in colored surface. So this is what we use for our analysis. And now, if you have three different geometry, you have the three different paths of loading. One is here. I've said opening by instrument. This is the testing machine which we use here. Actually, we start with 5 millimeters. It's almost very quite narrow. You need, of course, highest load because it's almost straight will be ones, yeah. But you see also this couple of millimeters still open. And here now we want to put the follow this opening. This starts from 0 to the maximum load. For 10 millimeters we got to 1, and then already come here in plasticity range. That means when you once loading, then you will never come on the same point back. And so if you're loading in this way, you will have, let's say, low cycling fatigue behavior locally. And also, if you look here, it is for 50 millimeters. You have, of course, it is the very close profile, and now often we need a lot of, let's say, a huge displacement up to 25 millimeters for opening to have the stress, to have the opening stress about more than 1 kilometer. So this is what we have experimentally, but now we want to have numerically. Numerically, we make here the step. And it is difficult to talk about now the displacement, because displacement will be the result of load which you put in the abacus. So we now start with the loading from 0, and this is actually our position, which we 0.5, 0.6, and so on this point. And you can see here is the number of the newtons which we achieve in this point. And this is our loading characteristic of cycling loading of this specimen. And we want to now to get the stable behavior. It is the next slide, also for animation. Maybe what have you know? Try. Actually, you will see how actually to generate the opening stress S11 in this middle point, in this tip. And also we will follow this behavior. This is from numerical. But here I can actually show you the comparison now from numerical work. Yeah. This is the curve which we got by for the 5 millimeter specimen. And here also for 10, and here also for 15. So this is actually what we use. We calculate for finite element modeling, and also we now will use these parameters for compare with the instrument. So this is actually our result of loading. But now we need to calculate the stress. The stress we took from the model, and for 5 millimeters you have this loading path. And here we have that our load, for example, is mainly it's total load, but consists two. It consists the membrane strain, so for tension, and this one here, it's the light blue. It is the bending. B is bending. And the total is actually just superposition of membrane and the bending for this small point. So it means that you got about 800 megapascals, but you can say that actually tensile load has lower influence than bending. And this is really the reason why when you establish model, I will show you later, just you concentrate on the bending, how the bending actually behave. So here we did the same for 5 millimeters, for 10, of course, then is the more close the bending, then you have the more displacement for the same load level. And also you can see that, for example, for these 50 millimeters, actually the membrane is almost constant, something a little bit more than 0, and mainly is just the bending stress, which is contributed by displacement. So now we want to consider in our analysis the loading point for different for specimen which was 10 millimeters bended. And here we now to follow for opening stress. This, while we not start from zero, it is influence actually of residual stresses. But these residual stresses we got also from numerical. So when you start bending, yeah, to make the flat specimen to bend, then you generate residual stresses which are tangent. And this is here, you can see, for example, in one point, we make some section here, and this is the actually from half the specimen, from zero it was here, and this is from 10 millimeters. All of that was 40 millimeters. And you can see that actually this stress, it is on the edge, and this is in the middle, yeah, that on the edge you have actually increasing, yeah, and then these results you can see on this edge, it's almost constant, and you got about 1,000, less than 1,400 megapascals for stress for different, actually you can see for these different steps which I explained. The last one was, the highest was 1.8, 1.9 kilonewtons, so here you have, oh sorry, 2.8 kilonewtons, this is this red line. And you can see that actually different loads were 1 kilonewtons, but almost the same stress on the point, because materials is go actually, it's numerical results. Materials is actually takes the hardening and goes deeper in the material when you start to simulation this opening bend. So this is also quite interesting result, but we are now going to see what's happened during the fatigue loading. And here you can see for only one single point, which we are considered here. This is in the half of specimen. It's the H. The second half is here. So this point is critical. We prove that in the middle we have crack initiation, and our residual stress when we start with, for example, with fatigue, is here in megapascals, and this actually this side which we have here, this belongs to this curve, but we start to loading. Yeah, we start from the zero to load, and actually we going to this curve of loading. The slope is like linear elastic until the point when you have additional, let's say, hardening, and then you got a plateau for microstructure yield here. And then if you're doing now the opening and let's say unload, then your unload also goes to this line. Here is actually the load in the displacement. It is this line from the origin, from zero, this blue one. But this is what's happened in the same time with the stress in this point, that you start to unload down. And if you're going to repeat this one, for example, with this straight line, that will come in this point, and then you go here. So you have always some shift this will happen. So this is quite unstable fatigue process which you have here, but we want to get what's happened in the model now. And here is the result that different 10, 5, or 50 millimeters bend may change the slope of beginning of loading. So it's this is, for example, for only 50 millimeters, you have this. Sorry, for 5 millimeters, you have this slope. Yeah, for 10 millimeters bending here, and for 15 here. So you come with different bending. And now this our characteristic which I showed you before. Actually, we will follow this bending for our calculation in model. Here is we calculate this stress which we have from the force. Then we have the bending stress. So we calculate for the moment. And you have here for the moment for 15, but first loading, then you have, this is now from instrument data, displacement and load. You have the second, you have the third for 50 millimeters, and you can see that each actually cycle, which you do repeated, has a different behavior, different slope, because you have already some classification, and of course you cannot come to the same point as before. We did also for 10 millimeters and for 5 millimeters, we have only two loading cycles. First one, and then when you repeat second, it's almost, because it gets flat, yeah, your bending moment decreases because the tensile force decreases. It becomes more flat. So this is now that with this displacement, we want to calculate how it behaves, and now I'm going to present the model. This is here what we have in the moment, and this is here what we have from final element computation. So this is combining material properties with the final element computation in order to determine the behavior of loading, to determine the loading amplitude. Because amplitude is not what we assume that will be just with simple calculation, but it depends on the behavior of material. So here we have the stress on this side, opening stress, and here we have the moment. Moment was this blue violet line, and here you have already start with residual stresses, and this is the linear, let's say, loading path. So you start from here, and immediately you have this stress, and when you come in this point, you are already with this opening displacement, you are already in this plateau, and if you continue, you will stay on this plateau, remain. So if you're doing now the unloading from this point, you go down, for your results of final element computation is going to give you this, let's say, relaxation. And if you repeat this, you will see that from this line, say, you will got the different unloading curves, because you always have some different shift in plasticity. Then the second thing is, now we want to combine with experiment. Yeah? Why? Because first we have this movement here in this point. What is this actually? This has happened because you have some clearance, you have some imperfection with the start loading, and then when we start actually with this, let's say, small load here, then you go to this linear. This linear should be the same for loading respect to the moment. So this will be your load which we have, should be the same line. Let's say start from here to up. But now we want to see what is exactly our amplitude. We use theoretically error point 1, 10%. It's a ratio between minimum and maximum stress, load. But our effective amplitude is different because material already had transformation, already you have residual stresses, so you cannot start with 0. You always should consider this load. And what we did with this here to make the linear line, and if you know that this linear is maximum, you come on this loading path from final element computation, and you got what is the value of your stress here in this point. And then when you're doing unloading with this curve, which is actually, let's say it should be similar like this one, you come from this point which is corresponding to your ratio loading, yeah? Because you start from this ratio to movement, and then your actually amplitude, loading amplitude is between, let's say, 600, 500 until 100, 1050, 1150. 1150. So you have this amplitude. So not this one, which will be, for example, usual, but because it's material brittle form, you got this value. So we can actually now to repeat also for another curve, for example, from this one here. Also, this is similar, this loading part, and then also for this material, you got these results. because this amplitude is varied, and we now calculate the number of cycles. So if you start, when you start once the loading with this amplitude, you have this R ratio which you have, and you don't, if you stop, you will change, because when you will go with the loading, you will have the difficulties, but if you will use always the same, and not go lower than this and not upper than this point, you can say that this is my constant loading amplitude with ratio, which we can calculate from ratio between this stress and this upper stress. And what we did, all these results we collected here, and actually this is results which we got from specimens with 5 millimeters. It is the round light blue, and cubes are for 10 millimeters and triangle for 50. We got these results which each corresponding to real stress ratio. And when you put like that, you got something like Euler curve, let's say SM curve. And here, for example, this point, we have no fractures, and it means that we got fatigue limit, which actually fit the fatigue limit of this material. So this is what we actually got from this combination of loading. I can say that the deformation of this material, metastable austenitic material, it's obvious that on room temperature you can get by deformation, different level of strain, applied stress and stress. We go to different strain, and from different strain we can calculate the magnetic phase concentration. And also we found that we have good correlation between the fatigue limit of this material. Doesn't matter which the combination. So I think that these results actually confirm that something what is already known, but this model provides the different view to the behavior of the material. So that's fine.
Thank you very much.
Thank you.